Hello, and welcome once again to FlippedHarber for Physics. In this video, I'm going to go over some practice problems from section 2.3 of the textbook. These practice problems are found on page 39, and they're numbers 9 through 13. Number 9, it says describe the motion of the car shown by the graph. Now you should really be looking at the figure 2-13 in your book so that you get an idea of what this graph looks like. Some important features of the graph to note. The initial position of the car is at 125.0 meters. The car has a negative slope, which means that it's moving backwards, and the slope of that line is negative 25 meters per second. So a nice answer for this question, describe the motion of the car, you should say that the car is moving backwards at 25 meters per second. You probably could have skipped the actual calculations on this one, but you definitely need to understand that when you see a negative slope in a position time graph, that means that the object is moving backwards or towards the origin. Alright, let's move on to number 10. It asks us to draw a motion diagram that corresponds to the graph. So I'm going to need a number line first of all. Now I've numbered this from negative 75 all the way up to 150 so that it's going to be able to include all the information from our position time graph. I need to go ahead and label where the object is starting. I like to usually do this by putting a t equals 0 seconds. Now since they asked for a motion diagram, I actually need to draw a car. Okay, I didn't draw this car. I went and found it. It's clip art. But hey, sue me. So now all we need to do is pick an appropriate time interval and draw where that car is after every time interval. Now it was pretty easy for me to just copy and paste this car as many times as I want. So I decided to go ahead and do it for 1 second. Every single car you see represents 1 second later. If you pay attention to it, the little guy is facing to the left, so he's driving towards the origin, and in every second he covers 25 meters. Now, this probably would have been a little bit of a pain in the butt for you to draw a little car every single second. If you want to, go with a slightly larger time interval, maybe 2 seconds, and you'd only have to draw every other car. Don't get too crazy with this. Don't decide, oh, well, I'll just draw a car every 5 seconds. That's too big. Number 11 says answer the following question about the car's motion. Assume that the positive D direction is east and the negative D direction is west. Now this did match up with my motion diagram. So part A, when is the car 25 meters east of the origin? Part B, where is the car at 1 second? So, when is the car 25 meters east of the origin? Well, I can just look up in my graph that it's 4 seconds. Where is the car at 1 second? Well, now I start down on the time axis and I move up to my graph and it's 100 meters east of the origin. Notice I was very complete in my answer here. I didn't just say that it was 100 meters. I went ahead and used the information about east and west in order to give a very complete answer. 100 meters east of the origin. Alright, let's move along. Number 12, describe in words the motion of the two pedestrians shown by the lines in figure 2.14. Assume that the positive direction is east on Broad Street and the origin is the intersection of Broad and High Streets. Again, you should be looking at this figure so that you know what I worked off of in order to answer this question. Pedestrian A is starting west of High Street. Again, I'm looking at time 0 to answer that, and walking east. Pedestrian B is starting east of High Street and walking west. Now that's some pretty good information, but I can add to this if I just look across my graph and try to notice more features. The two pedestrians pass each other just west of High Street. So where do those two lines cross? Pedestrian B is walking slightly faster than pedestrian A. Now this is subtle. The way that I know that pedestrian B is walking slightly faster is because of the slope of the line. Let's take a look at number 13. It says Odina walked down the hall at school from the cafeteria to the band room, a distance of 100 meters. A class of physics students recorded and graphed her position every 2 seconds, noting that she moves 2.6 meters every 2 seconds. When was Odina in the following positions? So we want to know, when was she 25 meters from the cafeteria and when was she 25 meters from the band room. Now, later in the problem, they ask us to make a position time graph for Odina. One way to answer the questions from A and B would be to actually make that position time graph first. But I decided to go ahead and do the math. We know that her speed is 1.3 meters per second. All I did was take a distance divided by time calculation. Now, in order to find her time, I take a distance and I divide by her speed. So since I want to know how long it took her to get 25 meters from the cafeteria, that's my distance. Divide by the 1.3, and I find out that it took her 19 seconds to reach a distance of 25 meters from the cafeteria. Now, in part B, 25 meters from the band room means that Odina has walked 75 meters. So I switch up my distance from 25 to 75. Divide by the 1.3, and I get 58 seconds. Now let's take a look at that graph showing Odina's motion. Here we go. So the distance from the cafeteria is our position, and we see that it starts at 0, and it's a nice straight line all the way up to 100 meters away. That's when she reached the band room. Alright, so we're all done. Hope you enjoyed it. I'll see you in class, and I'll see you online.